Welcome to this explainer on interfacing and communications. Today we are looking way past the glass and metal of your everyday devices. We're going to explore this literal microscopic metropolis operating inside and look at the absolutely crucial infrastructure that keeps our whole digital world from just crashing down. So let's jump right in.
So here is a really fundamental question. How does a hyper-fast, genius CPU communicate efficiently with something as painfully slow as a keyboard? Well, it turns out this right here is the fundamental bottleneck of all computer engineering. Think about it. The CPU is in there processing millions of complex calculations in mere nanoseconds. But the outside world, your peripherals, your sensors, they operate at a completely different, much slower scale.
Okay, let's dive into this speed gap, because it is massive. We're talking CPU processing speeds measured in nanoseconds versus I/O device speeds operating in milliseconds. To put that into perspective for you, if your super fast CPU actually had to sit there and idle in real time, just waiting for you to strike a single key, it would be the human equivalent of waiting literally years for a reply to a text message. If it worked like that, our entire digital metropolis would completely grind to a halt.
So to solve this major bottleneck, we first have to classify all these different endpoints into input, output, and storage devices. And we don't just do this to give them neat little labels. This categorization completely dictates the underlying engineering approach. Like a massive storage drive that's pushing gigabytes of continuous block data, that's going to require a drastically different connection strategy than a mouse or a keyboard that just sporadically sends a few bytes of character data at a time.
Now, the really ingenious solution to this crazy speed mismatch lies in something called I/O modules. See, because of that massive timing gap we just talked about, plus totally varying voltage requirements and the completely different data formats that all these external devices use, they literally cannot be wired straight to the CPU. It just wouldn't work. Instead, we use these dedicated I/O modules to act as official hardware translators. They step in, buffer the data, and manage all those erratic external flows so the central processor never actually has to slow down its own pace. Back in the day, we relied on an older technique called programmed I/O. And I want you to imagine sitting by your front door all day long, obsessively checking the peephole every single second just to see if a package arrived. That is programmed I/O. It's a terribly inefficient, exhausting waste of resources for a CPU to constantly micromanage an external device like that. So the critical architectural upgrade to this was interrupt-driven I/O. This is so much better. It's like just going about your busy day and getting a quick text notification when the delivery driver is finally at the door. The device only taps the CPU on the shoulder when it actually has data ready to go.
But wait, what happens when you're, say, furiously typing on your keyboard while simultaneously rendering a massive 4K video and downloading a huge file all at the exact same time? Now you've got multiple devices signaling the CPU all at once. Without a system, it'd be total chaos, right? Well, that is exactly why we rely on vectorized and prioritized interrupt structures. Think of them like highly efficient triage nurses at a really busy emergency room. They step in and instantly organize the chaos. They identify exactly which hardware line is calling, that's the vectorized part, and then they determine which signal demands immediate attention, that's the prioritized part.
Now, as great as interrupts are, they aren't exactly a flawless magic bullet. There's a hidden tax here called interrupt overhead. Imagine you're trying to write some complex, highly optimized code, right? But someone keeps tapping you on the shoulder every 5 seconds with a completely mundane question. You aren't going to get much actual writing done. That constant context switching is a severe performance penalty for the CPU. It burns precious cycles just trying to save its current state, push registers to the stack, switch tasks, and then go back, all of which ultimately slows down the processor's actual primary workload.
And that brings us to a really massive, fundamental leap in computer engineering: direct memory access, or DMA. If we go back to our city analogy, and the CPU is the incredibly busy mayor of our computer city, well, DMA is the ultimate delegation tool. Instead of the mayor, the CPU, personally ferrying every single block of data from a hard drive over to the system memory, DMA allows I/O devices to transfer large payloads, like entire pages of memory, directly. It completely bypasses the CPU. It's basically like the mayor just hiring a dedicated logistics manager exclusively to handle all the bulk data transfers.
So how does this delegation actually work? It happens in 3 beautifully efficient steps. First, the CPU issues the command. It tells the DMA controller exactly what data to move and exactly where to put it.
Second, the CPU just goes right back to its high-speed calculations, completely ignoring the I/O, while the DMA silently transfers all that data across the system in the background. And then third, the DMA simply sends a single interrupt signal to the CPU when the entire massive job is finally finished. It is a brilliant way to drastically free up the CPU and maximize the overall system throughput.
But we can actually go faster. Modern computer architecture pushes this whole concept even further with something called direct cache access. If standard DMA is a dedicated data manager, direct cache access is like handing that manager the keys to a VIP fast lane. Instead of just writing data out to the main system memory, it allows incoming data to be injected directly into the CPU's ultra-fast internal cache memory. We actually see this implemented today in high-speed network interface cards inside modern enterprise servers. It's a real game changer because it slashes latency to almost zero and accelerates those data transfer mechanisms to absolutely blistering speeds.
All right, so now that we know how these devices negotiate, let's look at the physical highways they actually travel on to get around, the buses. Generally speaking, we see two distinct synchronization methods here. First, we have synchronous buses. These run on a very strict central clock. It's kind of like a highly optimized transit system where the trains leave exactly on the microsecond, every single microsecond. It's incredibly fast, perfect for short traces directly on the motherboard. Alternatively, we have asynchronous buses. These don't rely on a global clock at all. Instead, they use device handshakes. So one device basically signals, "Hey, I'm ready," and the other replies, "Okay, send it." This handshake method is awesome because it provides massive flexibility, perfectly accommodating devices of wildly different speeds on the exact same channel without running into any weird timing skew issues.
But here's the catch. Whether a bus relies on a strict clock or a flexible handshake, at the end of the day, these are fundamentally shared highways. Without some kind of specialized traffic controller, you'd have catastrophic data collisions that would just corrupt the entire system. Enter bus arbitration. This is the absolutely vital control mechanism that determines exactly which device gets to claim that shared bus next. Without bus arbitration acting as a strict traffic light and rigorously managing the flow, multiple devices firing data at the exact same moment would literally paralyze our entire digital city. And the crazy thing is, this field never just stands still. Hardware engineers are out there constantly pushing the limits with new interface standards. We're talking things like PCIe Gen 5, Thunderbolt, and Compute Express Link. They are relentlessly widening these data highways, upgrading the protocols, and innovating new topologies to definitively solve that eternal bottleneck we talked about between these brilliant, ever-scaling processors and the much slower physical world.
Which ultimately leaves us with a pretty provocative question. As artificial intelligence continues to accelerate, as graphics rendering becomes literally indistinguishable from reality, and as the global generation of data just absolutely explodes, can our physical I/O interfaces actually keep up? Understanding the fundamental principles we covered in today's explainer, from interrupts to DMA to bus arbitration, is exactly how tomorrow's engineers are going to find out. Thanks so much for joining me today, and keep exploring those incredible hidden cities operating inside your machines.